Hello everybody, I'm Gregory Lee, a software engineer at Quantsite, and I'll be talking today about accelerating image processing using Dask and scikit-image. For context, biological imaging applications such as medical imaging and microscopy are generating increasingly large data sets as spatial and/or temporal resolution improves, and this large amount of data presents challenges in efficiently analyzing and publishing results in research applications. As a quick overview, I'm going to be covering how we can accelerate scipy.nd image functions via Dask-image, use of scikit-images, apply parallel, and blockwise processing of images larger than the CPU or GPU memory. And I'll additionally be mentioning a couple of GPU-based libraries through CuPy or Rapid's cuSim that can also help accelerate these kind of operations. So Dask-image itself takes advantage of the fact that many image processing operations are amenable to blockwise processing using Dask's map blocks or map overlap functionality. And so this library basically uses that wrapping, providing a lot of functions that match SciPy's API and behavior, but they're pre-configured to run with Dask arrays as input in a blockwise fashion. So for things like convolution, thresholding, morphology, this is pretty straightforward application of those map blocks functions. Some other functions can be a little more complicated, like say affine transforms, where we have to work out which blocks of the output correspond to which input blocks, or things like FFTs, where we may currently have to rechunk into a single chunk along the axis where the FFT is being performed. So we're going to look a little bit today at benchmarks for Dask-image. Just some practical tips in getting good performance are the image blocks themselves need to be somewhat large in size, at least on the order of 10 megabytes or so, so that this basically not smaller than say 512 squared in 2D or maybe 64 cubed in 3D. And ideally you want the total number of blocks to be larger or equal to the number of CPU cores. And then a final consideration is if the function you're wanting to call in a blockwise fashion is itself also multi-threaded, you may want to see about disabling that multi-threading so that you don't suffer from a thread oversubscription or having many more times threads allocated than the number of processors. So looking at some benchmarks for some basic filtering operations like uniform filter, Gaussian filter, maximum filter, or binary erosion. The plot here is normalized to performance in scikit-image, so SciPy, not scikit-image, and SciPy itself is shown as 1 here, and then factors larger than 1 indicate acceleration by that amount. So Gaussian filter, for example, is running 5.5 times faster on this 10-core CPU when doing things in parallel with Dask-image. And this for somewhat large volume, 3D volume with a chunk size of 128 cubed. We can add GPUs to that comparison, showing here on a kind of a gaming class card from a couple of years ago that GPUs provide even a substantially larger acceleration than running in parallel on the CPU. And this is now shown on a log axis here. So some of these are more than a factor 100 faster. Median filtering was one filter that is accelerated particularly well in the CPU. The acceleration factor approaching the number of cores of the CPU, which is 10, so we're very close to what you might expect to be the maximal improvement you would see. And looking now at interpolation with affine transforms, I didn't see much acceleration when using a nearest neighbor interpolation for this particular affine, but going to higher order splines, I did see a substantial improvement in performance. And those spline transforms also accelerate very well on the GPU. So if we look now at scikit-image and its apply parallel utility, this is works similarly to the things done in Dask-image, but the user can provide any function and it basically maps it to blocks for the user without the user having to know the Dask API. So basically they apply a function, its keyword arguments, the input array, and then some chunk size, and it will configure Dask and run the computation, returning a NumPy array at the end. And this can be used with quite a few functions in the scikit-image API, but we could always improve our documentation to make it clearer which ones are compatible. just for the purpose of this talk, I tried it out on a number of the denoising algorithms available through the restoration module. And if I look at these, I notice a couple of them are doing worse when applied in parallel than when not applied in parallel. And this turned out to be an issue where the underlying Python code doesn't release the global interpreter lock, which is a Python feature that can prevent multi-threading from being able to be used. And it's a fairly simple case of adding this no-GIL context into that code, which then enables those to run at a higher acceleration factor. But these two functions are currently, that's not in the released version of the library, but it should be in our next release. As a final use case, I want to show application to a high-resolution ex-vivo MRI scan that has approximately 10-fold higher resolution along each axis than a typical clinical scan, and this corresponds to raw data that's publicly available and is described in this publication down here. The data set itself is 4 fairly large 3D volumes, where these 4 each have slightly different MR contrast settings, and its total shape of this 4D data is about 23 gigabytes once you convert to a single precision float format. And I'm going to be looking at applying a denoising algorithm, which I don't want to go into the details here, but it works similar to wavelet denoising, where you apply some transform to a sparsifying domain, apply a threshold, and then do an inverse transform. But in this case, the transform is more redundant than standard wavelet with a factor of 16 in 3D. So our data becomes nearly 400 gigabytes in the transform domain. It's too big to fit in our CPU or GPU memory. So the approach used is to use naiBabel to read in the medical imaging data and save it back out as a ZAR array that's stored on the disk in chunks. And we can then use that as the input to our Dask array map overlap function, which can use a similar chunk size, and we will only need to load chunks into memory on demand. So if we run this map overlap with a single threaded schedule, we'll only be loading basically the current chunk at a time. And the transforms used here are described in this publication, and they take about a day to run serially through all the blocks in the CPU, or about an hour on a GPU implementation. So if we look what this data would look like at a typical downsample to a typical clinical resolution, you would see an image like this for a kind of mid-sagittal view of the brain, whereas we have this much higher resolution in this data set, but you can see some graininess here that's just due to the level of noise still present in the data despite the long acquisition time. This actually was acquired over a period of about 4 days of contiguous averaging, which is why this is not the resolution used in the in vivo clinical exams. And so if we apply denoising, it cleans up a lot of this graininess, and we can see that more clearly if we zoom in on a couple of ROIs, this one up near the central sulcus at the top of the image, or one down near the thalamus. So in summary, any of the following software packages are, they're all open source. They welcome community contributions, and we'd be very glad to hear from you there. And I want to briefly acknowledge some funding on the scikit-image side to work on these sorts of things from CZI. Thank you for your attention.